I'm going to talk to you about search on Hadoop today. And I put together a presentation. We have a pretty limited amount of time. It's a pretty wide area. But I put together a presentation to give you some insight into why we need search on Hadoop, what we can do to facilitate big data capabilities around search, what architecture we put together at Cloudera to provide search. Also, what challenges we face, both in terms of near real-time and batch-oriented use cases. Conclusion and some Q&A at the end if people have some questions. I'll give some insight into how to get access to the code and try things out, look at documentation and online training, etc. So first off, why search? You've got a large framework for Hadoop. It's a large ecosystem. There are a lot of different components. There's a lot of information feeding into the system. We've got a large pool of data co-located with data processing. So you can run MapReduce jobs to analyze your data. You can run Hive jobs. You can run Impala jobs. You can run SQL queries, etc. How do you find things? It's a lot of information that is being put into your Hadoop cluster. At the end of the day, how do you get access to that stuff? How do you have a single framework around security, a single set of system resources that you can take advantage of in a flexible way, both in terms of running these jobs, but also doing the search capability. Also, how do you have a single management interface to manage all these things and put everything together in a reasonable way so that you can use it easily. So from a user perspective, what are our end goals? So we have all this data, and people want to find things. They want to explore the data. So you might have a large number of files, a large number of records sitting in your HDFS cluster. How are people going to find that over time? On the first day, it's fairly straightforward. On the second week, it's fairly straightforward. But as time goes by, more and more information is being put into the cluster. How are people finding that information? How are they navigating through it? What if I want to find the healthcare records from 2 years ago and correlate that for a patient that's in the hospital today? How do I correlate the information? So if I've got all kinds of different information, how can I correlate? Can I correlate some patient records with other billing information that the hospital might have? I might want to use search. Well, I might want to use MapReduce, but the number of people who actually know MapReduce is pretty small. It's a specialized community. If we expected everyone to run MapReduce on these things, we wouldn't see a lot of usage on that data that we're storing and moving around fairly expensively. You probably have more people who know SQL than know MapReduce, so that's going to widen it out a bit. So we have people who can run SQL queries and analyze the data and get some sort of information back. They can run queries and say, let me look at the information from last year based on this SQL query, let me look at it now. However, the number of people in an organization who know how to search today, pretty much the whole organization. Everyone knows how to do searches. So providing that search capability where people can just run a very simple textual search, get back some records, look at the information, do some correlation, is super valuable. At the end of the day, what is Cloudera Search? So it's a full-text interactive search with faceted navigation. What that basically means is you can run text-based searches just like you do on any search engine site and immediately get results back. You don't have to wait for your MapReduce job to run. You don't have to wait for your query to run and then look at the results back. And it's given to you in an interface that you're pretty familiar with. If you're using Amazon or if you're using LinkedIn to run queries, if you're using any search engine to run queries, you're pretty familiar with what you enter in and what you get back. We also want to provide the capability of doing batch, near real-time, and on-demand indexing. So if you've got a large corpus of data, you probably want to do batch-oriented processing on it. If you've got information that's streaming in, then it's critical to meet certain SLA requirements such that the information will be indexed and queryable within a short period of time. Let's say you have a support organization, customers are calling in, hey, my ID is XYZ. You might want to be able to search for that to see what's going wrong in the system right now for those users. So you wouldn't want to use batch in that case, you want to use near real time. So we've taken Apache Solr. It's a very mature project. It's been around for quite a while. It's based on Lucene, which has been around for even longer. And we integrated that with Hadoop so that you can run it on top of your HDFS file system, take advantage of all the capabilities. You've got all the data there. You can integrate it with other systems that you have, like MapReduce, like Flume. It's a separate runtime, much like MapReduce and Impala and some other systems. And it's open source. It's 100% Apache, 100% Solr. So if you're familiar with Solr, and I've talked to a lot of customers who say, oh yeah, we already do search. Go talk to Joe. He's our Solr expert. You're going to be able to take this thing, plug it in into your existing infrastructure, and take advantage of it because we haven't written anything from scratch. We haven't changed anything. All the APIs are essentially the same. So if you have a GUI that can run against Solr today, you can plug in this solution, and it runs exactly the same from an API perspective on the query and the indexing side. So I mentioned some challenges. These are the challenges that my team faced while we were trying to implement this capability. And I'll show you some of the things that we ran into and what we did to resolve these problems. There's a few different areas. One is around scalable and reliable index storage. So Solr is reading these data files and it's creating an inverted index and index so that when you run a query, it can quickly give you results. So you need to store that someplace. You might need to back it up, it needs to be reliable, etc. We'll talk about that. Here, real-time indexing. So as information is coming in, some category of information that you have coming in might need to be searchable right away. Some you might just stash in HDFS and process it later. That's more the batch-oriented use case. Or maybe you acquire a new company, or a new part of your company becomes interested in the capabilities that you provide. You have a large data set, you want to integrate those, you use batch. Typically, you want to use batch-oriented processing for that. The other is around usability. How do we provide these facilities? So we're going to build this system out. And at the end of the day, we have to support that end user who wants to run queries, have a fairly familiar interface to run those queries and see the results. So the first part is around the scalable index storage. So we've taken Apache Lucene and Solr. So Lucene, in case people aren't familiar, so Lucene is a full text search library, so it does indexing and it supports the querying of the index. It has a syntax for doing that, etc. Solr is a web service that will run on top of Lucene, so it integrates those Lucene capabilities and it provides an API for running queries. So you can use JSON or XML, etc. If you run the query, see the results come back. It's a web server. That's been made into a distributed system through the use of Solr Cloud. So Solr Cloud uses Zookeeper to coordinate a number of Solr nodes that are working in console. So let's say you have a very large corpus, a large number of documents. It's too large to store on a single server. You need to partition the information. That's where Solr Cloud comes into play. And it can take that corpus and break it up into multiple partitions, distribute it again across a number of servers. When you run a query, it does like scatter gather. So it runs the query on multiple machines, collects the results, aggregates them back together, and shows you a single set of results. We're currently using Solr 4.3, which is the very latest version of Solr, and Lucene. We're actually very active in pushing for upstream releases. Mark Miller, who's one of the primary contributors of Solr Cloud, works for Cloudera, and we've been pushing on a lot of development. So how exactly, or what exactly do we change Lucene and Solr to enable it to run on top of HDFS. So Lucene has something called a directory abstraction. That allows Lucene to say, hey, I want to read and write some files, but I don't really care how that happens. It's typically implemented for a local file system. What we've done is taken the HDFS client library and implemented an HDFS directory using this abstraction, which now allows you to read and write those files directly to HDFS. There have been some other solutions out there in the past that would write to a local file system and then copy the indexes to HDFS, maybe as a backup or for reliability purposes, recovery. But we actually read and write directly to HDFS. So all the capabilities that HDFS provides you, like reliability, not really worrying too much about provisioning because you have a large cluster, statelessness of the servers because you can start up a Solr server anywhere in the cluster now and access the data on that distributed file system. Those things all essentially come free now as part of integrating with the HDFS client library. And again, we're writing those files directly and reading them directly from HDFS. Another piece is the directory factory abstraction. So we need a way of plugging into Solr, into that Solr service. We need a way of plugging into Lucene and saying, hey, don't write to the local file system. We want you to use this directory in HDFS. There's also some caching that goes on, some other tuning parameters that have to happen. So all those things happen in your directory factory abstraction pattern. And you can configure that within Solr. And now you're up and running on top of HDFS to keep it ready. This is like a very short list of some of the features that we worked on as part of the Solr community to provide this functionality. So all these things are going back to the open source community. Nothing's proprietary, nothing's held back by Cloudera. So we've been working with us in the community to provide changes to support this capability around HDFS interaction. I won't go through everything today because we're in a pretty short time frame, but if you grab the slides later, you can look at these in more depth. But they're all essentially around make the server work better with a distributed file system, which typically doesn't do. It typically runs the whole file system. Again, this is a very short list, many other improvements and other changes. So now we're on to how about the distributed system. What does that look like? So we know how to redirect from HDFS. What's our architecture going to look like in terms of the distributed system? So we have our Hadoop cluster. We have Solr Cloud with the Solr instances, the Solr servers that have a Lucene library embedded in them. We're reading and writing from HDFS on that Hadoop cluster. On the left-hand side, we have sources of information. So the Flume has events that are coming in, log messages, let's say. Those are things that we probably want to index in near real time. So as soon as those come in, since they're generated, we probably want to make them searchable by our users, maybe a support need. We have HBase. So you're reading and writing information into HBase in real time. You might want to, as those changes are happening, you might want to trigger indexing updates so that the rows that you're entering into HBase or the rows that you're updating to HBase become searchable immediately. On the flip side, from the near real-time side, you also have a batch use case where you have a large number of documents. Let's say you've got a bunch of new information, or something's changed. So your Solr schema has changed, your partitioning scheme, you want to change that, go from 5 shards to 10 shards, because you've got a lot more data over the last 6 months, more than you expected. You need to re-index it, you need 10 shards now instead of 5. That's a perfect use case for batch, and we'll look at that in a little bit more detail. So near real-time indexing with Flume. So if you're not familiar with Flume, it's a way of collecting events in a distributed fashion. It's highly reliable, highly scalable. You typically have these Flume agents running in your infrastructure somewhere in your data center, and they're collecting information. And they're forwarding it somewhere. It's typically being forwarded to HDFS. What we've done is made it so that you can take those events and write them directly into Solr. So we've done that through the implementation of something called the Northland Solr sync. So again, if you're familiar with Flume, it has an abstraction called sync. So it collects some information and it wants to write it to a sync. We've written a sync that allows you to take that information and write it directly to Solr in real time. So as those logs are being generated, as it's being collected by Flume, they're being written directly into the search engine, and you can do searches on them immediately. So there's a couple other things that probably have to happen as part of that collection. You probably need to do some ETL processing. Cloudera developed Cloudera Morphlines to enable that. This is actually something that shipped as part of the Cloudera Developers Kit. It's something that we have open sourced on, it's currently on GitHub. So the Morphlines library is essentially a Java library. The pipeline is very similar to a Unix pipeline, very analogous to a Unix pipeline. We have a number of commands that operate on the records. We get some records in, you can operate on those records, make changes, ETL processing, and then send the results over to Solr for indexing. Allow you to run queries. You might want to do this ETL processing because the original fields that you have in your event in Flume are different from what your Solr schema looks like. You can do that processing. Another source of new real-time information is from HBase. So you might be writing information into HBase, you might be writing records in there. You might want that information to be available for searching in your real time. Maybe you're writing documents in there, maybe you're writing patient records, etc. What we've done is implemented a service that can listen to those changes And as those changes happen, you can write it into the Solr environment and cause those documents to be indexed, and again, made searchable in real time. So actually collaboration between Cloudera and HDFS. HDFS you may have heard of before. They're the creators of the Lucene data management platform. It's actually runs on top of HDFS, HBase. It runs on top of HBase and Solr. And this is, again, it's a separate service that sits in your cluster. And it actually acts as an HBase replication list. Or in our case, we kind of lie to HBase and say, yes, we'll go replicate all this information. Let us know whenever something changes so we can go replicate it. But in our case, we actually write it directly in Solr and process the index. So we're taking advantage of an existing infrastructure around replication, an existing set of APIs that have been proven, battle hardened. And we're able to take advantage of that to capture that information. Again, we've integrated the Cloudera Morpholith library into this processing pipeline. So you can do ETL processing on those rows that come from HBase. So they can make changes, maybe a particular column family, you change some of the information into string in HBase and want to make it an integer or Solr. Maybe there's a timestamp that is human formatted date, you want an epoch number. I want to change something. You can do ETL processing as part of that pipeline. Again, this is also Apache license that's currently available on GitHub if you want to take a look. Now we get to the scalable batch indexing piece that I mentioned. So we have a large corpus of information that we bring into HDFS. For whatever reason you might not be using real-time indexing. Maybe you want to process the data every day or every week or every month. If you're only getting new information every month, but it's a large set of information. You probably want to do some sort of batch processing. So MapReduce is this extremely useful as well. So what we're able to do is run a MapReduce job, something that we provide, to ingest all those documents, process them, and then cause them to be indexed. The output of that is going to be written back into HDFS as a Solr Lucene index file. As we looked at from the initial case, Solr is able to rewrite indexes from HDFS, so that works out really, really well. Fortunately, though, you end up with sort of this two ends of the spectrum. You do either real-time processing, or you can do batch-oriented processing. What we wanted to do is try to bridge the gap between those two, so that if you wanted to run something every hour, you can still do so. You can run a MapReduce job, and the result of that MapReduce job would be merged into the Solr serving cluster as soon as the job is done. You wouldn't have to wait, you wouldn't have to start up a new cluster to read those specialized indexes. And that's something we're probably rolled up. So this is essentially what the MapReduce job looks like. Probably familiar to a lot of you who are doing MapReduce. Mappers are doing the extraction. So within the mappers, you're getting the document from HDFS. It might be a binary document, it might be an Avro record, it might be a sequence file, it might be a PDF file that you happen to be storing in HDFS. The first thing that you need to do is extract the actual text. What do you want to index? So you need to be able to extract that text before you can continue on with the process. The next piece that you need to do is the actual indexing version. So you want to take those documents and we're going to create indexes. And at the end of the process, you need to end up with a certain number of shards, or a certain number of partitions. So you decided, for my use case, my data set, I need 5 shards, or I need 10 shards. I need certain performance guarantees or have enough space to store all those documents and perform with reasonable performance. What we've done is implemented a number of reducer steps, a number of mapper steps that run as part of this job that allow you to essentially break those shards up into smaller subshards. So you're able to linearly scale the job across your entire MapReduce cluster. So if you have 100 nodes or if you have 1,000 nodes, MapReduce cluster, but you only want 2 shards at the end, you wouldn't want to have that inversion process only happen in 2 pieces. That would become a problem. So we do the inversion process across your entire cluster and then merge that down. And the number of steps in between the blue boxes, so that white box, you're able to actually control that through some configuration parameters. So there's essentially 2 parts to the job. And again, we create this job, we provide this job to you. You run it under existing data and it generates the indexes in HDFS as an output. But it's going to scan HDFS as an match a certain criteria. It's very much like a find operation. So So it's going, you're either going to tell it, look in this directory, or look for files that match certain criteria. Once it finds those files, it'll collect them. It'll then hand them off to the mapper in the research stage. So the mapper will be extracting all the documents that come. Maybe it's information from the last day, maybe it's information from the last month. That's going to scale across all the slots that you have available on your MapReduce cluster. Then the reducer will be indexing version. It's using Lucene to do that, and it's writing the indexes directly to HDFS using that HDFS directory abstraction implementation I talked about before. Go live. So real time is great. It's very low latency, but it's expensive because your Solr server is doing more than one job. You want your Solr server to do one job. You want it to serve queries with the lowest possible latency for your users. Serve the most number of users possible. As soon as you start doing the real-time processing, your Solr server is not doing 2 jobs. It's actually doing 3 jobs, but at least doing 2. So it's serving those queries. It's also doing that indexing version that we just talked about. You want to scale out to your MapReduce customer. On the other side, on batch-oriented, there's much higher latency, so you have to wait a long time if you're running at least a MapReduce job before you can see the results of that when you're at queries. It's much cheaper, right? Because you have an existing MapReduce cluster. It's very large. You can run these analyses very quickly or on a large number of documents. The go-live allows you to basically take the results of that MapReduce job and then bring it out into HDFS once the MapReduce job is done and merge them immediately into your live Solr service cluster. So this is a pretty major new feature that we've added to Solr capabilities. You don't have any downtime. You don't have to take down your Solr cluster, do some manual or automated manual process of merging these indexes together. You don't have to start a new Solr service cluster for these new indexes. You just point it to your existing Solr infrastructure, and it goes and merges the results of the job. Talked about usability. Cloudera created a few and then open source it some time ago. It's essentially a user portal for people to get access to things like running Hive jobs, running MapReduce jobs, running Lucene jobs, doing browsing the file system. It's a user portal, it's web infrastructure. If you notice across the top here, there are a number of applications. Search is one of them now, so we've added new support for search. So it's using those standard Solr APIs that I talked about before initially. We're just using regular Solr APIs. And because it's the same in our system, you can implement your solution using those APIs, standard Solr APIs. If you already have a solution that runs on top of Solr, you just run it on top. So we're using all standard APIs. And we're showing the user a set of results that are very similar to what they used to. So you've got a SERP with a set of search engine result page with a number of records. Each one of these is a template. So this is actually a template that you can configure. So here we're doing tweets as an example. If you run through the tutorial, you'll actually get a chance to try this out yourself against the live Twitter Firehouse. But we're basically formatting the results, and you can customize this to be anything you want. So if we have log files, log records, your own records, who knows what they are. You can format it and customize it to that. So this is the search results over here. Over on the left-hand side, that's the faceting capability. So if you run a search on LinkedIn, saw some great presentations from LinkedIn, earlier today. If you were to run a search on LinkedIn, you see similar results, obviously, people. On the left-hand side, you typically see faceting there around what was the company that the person currently works for, where did they work in the past. That's essentially what this faceting is doing over here. You're able to specify this as well. So you can say, I want faceting on the location that the person is reading from in this example. And then you can click on those links, like based in London. You can click on that and we'll refine it down so that you only see tweets from people that are in London. If you ran a query for you, and it would similarly show you facets, but it would only be for those results. You can then drill down. So from a data scientist perspective, from a typical user perspective, it's a very familiar environment that allows you to do navigation and drill down on that data that you have stored in HDFS, so that you can through Flume, HBase, etc. It's the end of the talk. Anything conclusion, we're currently in public beta, so you can download this stuff for free and try it out really easily. We have extensive documentation, we have user lists if you have any questions. There's some online training if you want us to go through and train you up on how to run this stuff. Cloudera Manager is also freely available. So if you have some machines sitting around, if you want to try this out, you can easily use Cloudera Manager to deploy things. Search is already supported by Cloudera Manager. So if you're using Cloudera Manager today, you can actually integrate search and try it out. It's also, as I mentioned, for free. There's also the quick start VM. So if you just want to download a VM and give it a try, everything's already set up. You spin up the VM, you'll come up with an environment where you can run through the tutorials really easily. Those tutorials are available in that documentation page that I mentioned. That's the conclusion of the talk. I appreciate everyone coming in today. Is there any questions that you have?
Very good talk. I thought the indices for Solr were sort of random rewrite patterns that you didn't get to just sort of do a log append kind of model for the indexes. So how does the HDFS directory adapter handle that?
Yeah, that's a great question. So in Lucene 3, that was the case. So there's some other projects that Blur, which is currently in the Apache HDFS. They kind of, the Blur project actually kind of led the way in terms of running Lucene on top of HDFS. And they initially did the work on Lucene 3. Now, when Lucene 3 wrote indexes, it didn't just do append only, which is all that HDFS supports. It would want to seek around in the file. And the reason for that primarily was to write the checksum. So it's pretty convenient to go to the beginning of the file and write the checksum after you actually write everything out. And what they did in Lucene 4 is they introduced the concept of codex, so it was much more flexible, the way that the on-disk format was for a lot of the files that they write out on the index, the segment files. And that was one of the changes that they made. So the default codec for Lucene is 10 only, so you don't need to do that. In the past, what we needed to do was essentially implement a virtual file system on top of the HDFS file, that when seeds happen, we kind of noted that, but we still kept the pending data in the file. When we read it back in, we would have to take that into account. But that's no longer necessary to change the Lucene. One of the reasons why we implemented it on top of Lucene 4, greatly simplifies all that. And now the code is actually, when you can see this, is all been contributed back to the upstream projects. If you go look at it, it's actually very, very straightforward the way it's implemented now. The directory abstraction itself is fairly straightforward. Open files, create files, new files, write information, read information. So that actually worked out really well. Has some other questions?
Yeah, we have a question here.
Hey, really quick talk. Could you comment on what's the capability of bringing content in that's not stored in the tool? Any capability? So in an enterprise, so there may be content that's not just stored in MapReduce, that you also want to search about, in addition to content that's stored.
Yeah, that's a good question. So the question is, what about information that's not necessarily stored in Hadoop? We've been focusing on Hadoop because our customers are all running Hadoop. What we've seen is they want to be able to use searching. So, and they typically have the information in HDFS. It's a large amount of information. They have to centralize. They're already using MapReduce instead of reviewing the process. What happens when the information is not stored in HDFS? So you have Flume. So if you want to capture information, those events, you can capture the information, send it in. You don't need to store that in HDFS. You can write it directly to your Solr instances. You're not interested in storing it in HDFS. Similar with HBase, a lot of people might use it as HBase. Maybe that kind of invalidates a particular question in this particular case. But so far, we haven't looked at JDC interaction or reading from SharePoint or reading from a wiki page. We don't have those capabilities, but there are other solutions out there. So Apache Manifold CF, which go get a system that can index documents and produce the standard Solr API, it's just going to work. So Manifold CF is actually a project whose cost of life is to go scan